Natural physics is a concept astrophysicist LeRoy developed that explains in down-to-earth scenarios how the principles of physics could have come about from observing nature. Each episode begins with a scenario, followed by an example to illustrate the application of these principles in futuristic research at the frontiers of science, such as LeRoy's astrophysics doctoral research, and then concludes with an exploration of how these same principles could have very well been used by ancient cultures and civilizations. Mathematics is naturally encountered and incorporated as the exciting and fun tool of science that it is. Science is the window into our amazing world of nature, and mathematics is the tool to open that window. Natural physics encompasses current, futuristic, and ancient physics, and ties them together by the principles of physics that are common threads running throughout each.
Oh, okay, brother. Down, I'm out. I'm down. You won, brother.
Got you, little brother.
Yep.
The force U is equal to my mass times my acceleration.
Is that why you're able to spin me around so fast?
That's right, little brother.
Aha. So acceleration, that's speed. That's fast. That's rapid, right?
That's right, little brother, and I got a lot of acceleration.
Oh, wow. And that force, that just means because you have a lot of mass. You're a big brother.
You got it, Dini. You got it, little brother.
F equals ma.
Excellent. Excellent, brother. And once again, what does that stand for?
Force equals mass times acceleration.
Excellent. Very excellent, little brother.
And that's an equation.
Hello there, I'm Osco, Balo's big brother and Dini's big brother. I'm the original natural physics saber-tooth tiger. My weight on this toilet seat is equal to my mass times gravity. And the weight of my tinkle is equal to its mass times gravity.
Good job, little man. Good job, little man.
Greetings, I'm LeRoy and welcome to the Natural Physics Experience, live from Costa Rica. We left off last week with starting to discuss the tracking of the betatron oscillations of protons as they circulate around a particle synchrotron accelerator. And as I hinted to, I believe there are implications in astrophysics. In order to track the betatron motion of the protons as they circulate around the booster synchrotron, we need to derive the equations of motion. We need to identify the forces that are responsible for the motion of these protons as they travel around the accelerator. And after identifying those forces, we need to come up with equations, mathematical equations that express the physical movement, the physical motion of these protons as they accelerate around these accelerators. as demonstrated by Balo and Dini. The fundamental equation in physics that describes all forces is force is equal to mass times acceleration. F is equal to ma. And as demonstrated by Osco, an example of one of these forces is the force of gravity. Force is equal to mass times gravity. F is equal to mg. The force of gravity is the one that we experience most in our daily lives. There's 4 known forces in nature so far. The force of gravity. Then there's the nuclear force that holds the nucleus of an atom together, okay? Keeps the neutrons and the protons together without exploding. And then there's the electromagnetic force, which is the force of attraction between negative and positive, electrons and protons. And then the 4th one is called the electroweak force, which involves radioactivity. Okay? Now, in a particle accelerator, the force of gravity is negligible. As these protons accelerate to very, very, very high speeds, yes, gravity, you don't even have to include it. But the predominant force here is the magnetic force that the quadrupole magnets exert on the protons as they travel through them. So let's go back to the paper and continue where we left off. Shall we? Yes, let's. Okay, here's the page where we left off at. And as you can see at the bottom of it, it says that's what we need to do. We need to derive the equations of motion for the protons as they travel through these quadrupole magnets. Okie dokie. This is a diagram that I did representing the quadrupole magnet in the booster synchrotron. And as you can see, you have 2 north poles and you have 2 south poles, okay? And what this diagram is showing, okay, remember the z-axis is straight down the middle of the quadrupole magnet, straight down the middle. Now, perpendicular to that axis, you have the x-axis, the radial direction, the horizontal direction, and you have the y-axis, okay? The axial, the vertical direction, okay? And as you can see from this diagram, you have the magnetic field, B, which has a horizontal and a vertical component, okay? It has a component in the radial direction, the x direction, and it has a component in the vertical, the axial position. Let me make sure I want to make sure I said that correctly. It has a horizontal component in the radial direction, the x direction, and it has a vertical component in the axial direction. Okay. And the fact is that these 2 components of the magnetic field, they interact with different parts of the proton motion. Now, again, visualize the proton as going the z-axis, okay? down the middle of the quadrupole magnet. However, if it's a little bit to the left of that axis or to the right of that axis, it's going to experience the vertical part of the magnetic field, because the magnetic field interacts with the charged particle at a 90-degree angle, okay? Right angle. So if that proton is deviated any bit to the left or to the right, of right down the center, it experiences the vertical part of the quadrupole's magnetic field. And to the converse, and you know I wanted to use that word, if the proton is displaced a little bit above or a little bit below the z-axis, right, in the vertical direction, the axial direction, it is influenced by B sub x, the radial, the horizontal, the x component of the magnetic field. How cool is that? So that's what this diagram is wanting to display. Okay? Now, we're going to get to our equations of motion. But before we do, what I just described about how the horizontal component of a quadrupole's magnetic field influences the vertical position of the proton, and how the axial, the vertical component of the quadrupole's magnetic field influences the horizontal displacement of the proton from the z-axis, expressing that dependence, the dependence of the horizontal and the vertical parts of a quadrupole's magnetic field on the vertical and the horizontal displacement of a proton with respect to the z-axis, the direction of trajectory of motion. It's expressed in what's called a power series, which comes from calculus. So here's our first encounter, crossing over from physics to mathematics, and how physics uses mathematics as the tool to open that amazing world of nature that physics provides. Here we go. Power series, okay? So here is the magnetic field in the x direction, the horizontal component, expressed in a power series. And again, this is from calculus, all right? Okay? And these are called partial derivatives, which we'll talk about later. But just, again, just think of these as mathematical tools, okay, that are used to try to get a handle on our amazing world of nature. All right. So this is called a power series, okay? And you have one for the horizontal part of the magnetic field, and you have one for the vertical part of the magnetic field, okay? Both are power series. Yeah, there's for Bx, there's for By. Now, because the time frame we're talking about, and again, these power series are to express mathematically the dependence of the quadrupole's magnetic field on the displacement of the proton with respect to that z-axis. How far is it up or below or to the left or to the right? Okay, that's what this power series is about. That's what this power series is about, okay? That's what that's about. It might look like Greek or some other language, but mathematically, it's trying to describe that dependence of the magnetic field using mathematical equations, okay? The dependence of that magnetic field on the position of that proton in the X and the Y direction with respect to the Z-axis, okay? Okie dokie. All right. So let's go to the next page, okay? Let's do that. Let's do that. All right. Now we get to the equations of motion. All right. You remember how I said that, and Balo and Dini and Osco demonstrated, okay, force right here in physics, force is equal to mass times acceleration. F is equal to ma, okay? Now, and here comes the physics derived from experimentation. The magnetic force that is imposed, that a charged particle experiences, whether it be an electron or a proton. Of course, proton having a positive charge, electron having a negative charge, but both equal. So the equation in physics arrived from experimentation is that the magnetic force experienced by a charged particle is equal to the charge of that particle times its velocity crossed with the magnetic field. Now, this symbol cross, it doesn't mean just time. It means it takes into account the three-dimensional interaction that's going on. Okay, so whenever you have a charged particle, whether it be an electron or a proton, the magnetic field is going to apply a force 90 degrees to it. Right angle, okay? And that's what this cross means. And because it's at 90 degrees, it turns out that the force between the force that a charged particle experiences from a magnetic field is going to be equal to the charge of that particle times its velocity times the magnetic strength of that magnetic field, okay? F is equal to EVB. Now, sometimes you see this equation expressed as F is equal to QVB, Q meaning the charge of the particle you're talking about. But if you're talking about a proton or an electron, Q is going to be equal to E, okay? The charge of an electron. All right. So again, you can see how we started with F is equal to ma. Force is equal to mass times acceleration. And in this case, that force, EVB, is equal to negative EVBY. And this is why that, oh, excuse the pun, this is why that is so. It's negative because the magnetic force in the plane is going to be trying to pull the proton more towards that Z motion. So you give it a negative. And here's where physics comes in, right? Experimentation. You got your mathematical equations, but you got to put the physical into it, right? You got to put the physics in it, right? A mathematical equation can be all kind of variables, numbers, whatever, but you got to make it real. You got to take that equation and you got to mold it into an equation that makes sense in the physical world. So there you go. So there's where the negative comes in, okay? And then you still got your charge. Now, because it says By, the reason for that is in a quadrupole magnet, remember, there's the horizontal part of the magnetic field and the vertical part. Okay. Well, straight down that quadrupole, okay, when there is no radial component of the magnetic field, then the total magnetic field is the vertical field. And conversely, when the vertical distance is 0, okay, there is no vertical component of the magnetic field. So it's all horizontal. So that's what these equations are saying, okay? It's just saying that in some cases, the magnetic field is all horizontal, and in some cases, it's all vertical, and that makes sense, doesn't it? Okay. So here we go back to the equation of motion. Force, mass times acceleration, is the magnetic force that a proton experiences when it goes through a quadrupole. And we shall continue. Okie dokie. All right. So what we have seen is that in a quadrupole magnet, the magnetic field has a horizontal and a vertical component. And the two quadrupoles together, two north poles, two south poles, they serve to try to collimate that beam of protons as they travel through the accelerator. And because the quadrupole magnets act just like a focusing optical lens would with a beam of light, you're going to have focusing and defocusing. You're going to have focusing, that z-axis, right down the quadrupole. You're going to have focusing in the horizontal or x direction with simultaneous defocusing in the axial or vertical y direction, okay? Both are going on at the same time. So I want you to see the mathematics that's involved, all right? We've already encountered a power series, which is from calculus. And then when we got to F is equal to ma, okay, you're going to see what that becomes. All right, so we shall continue next week. And again, at the end of this journey is my demonstration, my theory, that what I did in this project has implications with cosmic rays, okay? Highly energetic protons, much more energetic than are produced in the Fermilab Tevatron, but the principle of physics is still the same. So tune in next week. Same fat time, same fat channel.